Hello students, welcome to the channel Physics Regulars. In our day-to-day life, we are mainly depending on electricity. At home, at workplace, everywhere. But have you ever wondered how did the study of electricity begin with? The study of electricity is originated from the study of electric charges. So study of electric charges is the first step towards learning electricity. We, human beings, show almost same nature when we are standing and when we are moving. But electric charges are completely different. They show different nature when they are at rest and when they are moving. In physics, there are separate branches for studying static charges, that means charges at rest, called electrostatics, and there is separate branch for studying moving charges called electrodynamics. In this video, we are going to begin with the first chapter in electrostatics, that is electric charges and fields. First, we will see what are the topics we are going to study in this chapter. We start first, we study basic properties of electric charge. Then there is one important law in electrostatics, that is Coulomb's law, which gives force between two charges. After studying force between two charges, we study force between multiple charges. Then there is one important topic, electric field. Here we study electric field due to point charge, single charge. After studying electric field due to point charge, we study electric field due to system of charges. And then electric field lines, electric flux, and also electric dipole. And the last topic in this chapter is Gauss law and its applications. This Gauss law is also very important because using Gauss law we can understand how electric field originates from electric charge. Here my intention is to make you understand all these concepts in simple way. Now we are entering into the world of electrostatics. Many of you might have experienced at home when we accidentally touch current carrying metallic wire directly, we get sudden electric shock. But it is not a big surprise because there is electric supply connected to the wire. The interesting thing is sometimes we feel small electric shock when we touch metal door of a car, or when we touch iron rod of a bus, or when we touch metallic gate. We feel tiny electric shock, but they are not connected to any electric power supply. Why do we feel so? The reason is static electricity. We know every material is made up of atoms, and normally atoms are electrically neutral because atom contains equal number of positive and negative charges. Atom is electrically neutral. But when two materials or when two objects rubbed against each other due to friction, electrons from the atoms of one object may transfer to other object. Due to transfer of electrons, objects becomes charged. Object which loses electrons becomes positively charged, and object which gains electrons becomes negatively charged. And these accumulated charges stay on the surface of the object for small duration. These accumulated charges on the surface of the object are called as static charges. Suppose the object is metal. Metal is a good conductor of electricity. That means metal allows charges to move freely. When we touch the metal, these accumulated static charges flow through our body because our body is also a good conductor of electricity. Static charges flow through our body to ground. Here accumulated charges are called as static charges, and this phenomenon, sudden discharge, sudden movement of charges, are called as static electricity. This phenomenon is called as static electricity. Suppose object is insulator. Insulator do not allow charges to move freely. So accumulated charges stay on the surface for longer duration compared to metal. There is one common experiment. Comb your dry hair with plastic comb. After combing, plastic comb becomes electrically charged. Now bring the plastic comb near small pieces of paper. Paper pieces will be attracted towards plastic comb. This shows there are static charges on the surface of the plastic comb. Here accumulated charges are called as static charges and the process of attracting pieces of paper. This effect is called as static electricity. Another example is static charges on the computer or TV screen attracts more dust particles. And the powerful natural example for static electricity is lightning. Here more number of ice particles, due to collision between more number of ice particles, there will be friction. Charges will be transferred. Hence one side of the cloud becomes positively charged and other side becomes negatively charged. When too many charges collected, these charges suddenly move. This sudden discharge of too many number of charges cause lightning. It causes lightning. This is the powerful natural example of static electricity. Now let us take a look at the historical background of electric charge. Around 600 BC, a Greek philosopher, Thales of Miletus, made one observation. When amber is rubbed with fur, amber is a hardened gum from certain trees and fur means it is hairy skin of animals. When amber is rubbed with fur, amber got the ability to attract light objects like dry leaves and feather. This effect was observed by Thales. This is the first recorded observation of electric charging by friction. And there is a Greek word for amber, that is electron. Electron is the Greek word from which the term electricity is derived. This is the word electron from which the term electricity is derived. Many scientists made so many experiments for many years to study about electric charge. And they come to know different materials have different tendency to gain or lose electrons. For example, when glass rod is made to rub against silk cloth, glass rod has higher tendency to lose electrons. Hence, glass rod becomes positively charged. Silk cloth has higher tendency to gain electrons. So, silk cloth becomes negatively charged. Another example is plastic rod is rubbed against wool. Here, wool has high tendency to lose electrons. Hence, wool becomes positively charged. And plastic rod has high tendency to gain electrons. Hence, plastic rod becomes negatively charged. There is one more interesting example, that is glass rod. On rubbing glass rod with wool, glass rod becomes positively charged. Here glass rod, compared to wool, glass rod has higher tendency to lose electrons. So glass rod becomes positively charged and wool becomes negatively charged. If you compare these two experiments, here wool becomes positively charged, here wool becomes negatively charged. This shows the tendency of the material to lose or gain electrons is depending on with which material it is rubbed. Scientists made so many experiments with different types of materials, and they come to know there are two types of electrification. That means they come to know like charges repel each other and unlike charges attract each other. And also object becomes charged due to transfer of electrons. And one more interesting result is there are two types of charges. One is positive charge and another one is negative charge. We call it as polarity of charge. The property which differentiates the two kinds of charges is called polarity of charge. That is positive charge and negative charge. Now the question arises, how to identify whether the object is charged or not? If object is charged, how much charge does it carry? To identify charge on the object, scientists use a device called gold leaf electroscope. Gold leaf electroscope consists of metallic knob at the top and a metallic rod connected to the knob. At the end of the metallic rod, there will be two very thin gold leaves. Here gold is used because gold can be beaten into very thin sheets. When charged object touches the knob, charges flows through the rod and reaches gold leaves. Both the gold leaves get the same charge. Since like charges repel each other, gold leaves spread apart. Greater the separation between the gold leaves, greater the charge on the object. Hence, degree of divergence of the gold leaves indicate amount of charge on the object. In gold leaf electroscope, when charged object touches the knob, charges flows through the rod and reaches gold leaves. How these charges flows through metallic rod so easily? Can charges flow through every material? Based on this property, materials are classified into conductors and insulators. Conductors and insulators. Some materials allow charges to move freely through them. These materials are called conductors. For example, all the metals are good conductors of electricity, and our body, animal body, and earth is good conductor of electricity. And some materials, they do not allow charges to move freely. These materials are called as insulators. For example, wood, plastic, glass. In home appliances, we observe copper or aluminum wire carries current because it is metal, it allows charges to move freely. And this metallic wire is coated with plastic material. It is coated with insulating material because insulator do not allow charges to move freely. Hence, insulators protects us from electric shock. Then we come to basic properties of charges. We will study basic properties one by one. First, additivity of charges, then conservation of charges, then quantization of charges. We will learn additivity of charges. How to add charges? System contains number of charges. Then what will be the total charge on the system? Total charge on the system is given by Q total. How do we add numbers? In the same way, we can add charges because total charge on the system is equal to algebraic sum of individual charges. Suppose there are number of charges Q1, Q2, Q3 and so on up to Qn. Total charge on the system is equal to algebraic sum of individual charges. Charge is a scalar quantity like mass. But remember, mass is always positive and charge can be negative also. Hence, while adding, be careful. I will give you one example. Suppose there are charges Q1 equal to 5 Coulomb. Coulomb is the unit of charge and Q2 equal to minus 3 Coulomb and Q3 equal to 2 Coulomb. What is the Q total? Total charge on the system equal to algebraic sum of individual charges. Q1 plus Q2 plus Q3. What is the result? 4 Coulomb. This is how charges can be added. Additivity of charges. Next property is conservation of charges. Like energy, charges are also conserved. Charges can neither be created nor be destroyed, can be transferred from one object to another object. In the example of glass rod rubbed with silk, is there any creation of extra charges on the glass rod or on the silk cloth? No. Only charges are transferred from one object to another object. Hence, total charge in a system is constant. It is conserved. The total charge in an isolated system always remains constant. Isolated system of charges means consider in a considered system no extra charges are coming inside and no charges are going outside. In a considered system, the total number of charges remains constant. This is conservation of charges. No extra charge is created or no charge is destroyed. The third property is quantization of charge. Quanta means which is not continuous. Quanta means discrete. Charges are discrete. How? In a system, the charges are given by integral multiple of basic charge E. The smallest charge is E, the charge of electron, which is equal to 1.6 into 10 raised to minus 19 Coulomb. This is the smallest charge. In a system, the charges are integral multiple of basic charge E. Here there is no existence of half charge or 3 by 2 charge. There is no existence like that. Charges are always integral multiple of basic charge E. Like a packet of pen. In a packet of pen, you can get 1 pen or 2 pen or 10 pen. There is no existence of 0.5 pen, 3 by 2 pen. In the same way, charges are also integral multiples of basic charge E. This is about quantization of charge. The unit of charge is 1 Coulomb. 1 Coulomb is nothing but amount of charges flowing in a wire if wire carries 1 ampere of current for 1 second. 1 Coulomb is defined as the charges flowing through a wire in 1 second if the current is 1 ampere. And the value of basic unit of charge is 1.602 into 10 raised to minus 19 Coulomb. The value of E is 1.602 into 10 raised to minus 19 Coulomb, or 1 Coulomb equal to 1 by 1.602 into 10 raised to minus 19 E. It will give you about 6.25 into 10 raised to 18 E. This is the value of 1 Coulomb. Here is one example given in NCERT textbook. The example is, if 10 raised to 9 electrons move out of a body to another body every second, how much time is required to get a total charge of 1 Coulomb on the other body? If 10 raised to 19 electrons move from one body to other body for 1 second, how much time is required to get a total charge of 1 coulomb to other body. We will solve it. What is the rate of flow of charges? Rate of flow of charges equal to 10 raised to 9 electrons per second. And the charges needed is 1 coulomb. Equal to 1 coulomb. The time required to become 1 coulomb we have to find. We know that I will write it here. We know that E equal to 1.602 into 10 raised to minus 19 coulomb, or 1 coulomb equal to 6.25 into 10 raised to 18 electrons. Here we should find time required, time equal to, for 10 raised to 9 electrons it takes 1 second. 1 second. 1 second. For 6.25 into 10 raised to 18 electrons, how much time is required? Do the calculations. You will get around 6.25 into 10 raised to 9. 10 raised to 9 seconds. The time is in terms of seconds. You can convert it into years. To convert it into year, what will you do? Time equal to 6.25 into 10 raised to 9 divided by 3600 seconds into 24 into 365 days. How much you get? Do the calculations. You will get around 198 years. Hence, to become 1 coulomb, it requires 198 years. To transfer 1 coulomb of charge from one body to another body, it requires 198 years if the rate of flow is 10 raised to 9 electrons per second. Here we can observe coulomb is a bigger unit. Hence practically we use smaller unit, that is microcoulomb. Next is Coulomb's law. While studying Coulomb's law, we repeatedly say point charges. Here point charges means charged bodies. When size of the charged bodies is very small compared to distance between them, we consider charged bodies as point charges. For example, suppose these are two metallic spheres, charged metallic spheres of diameter 1 centimeter. If distance between them is 1 meter, then we consider these two charged bodies as point charges. When distance between charged bodies is more compared to their linear size, then we consider charged bodies as point charges. A French physicist, his name is Coulomb, he measured force between 2 point charges. He observed and measured the force between 2 point charges, and he found that force varied inversely as the square of the distance between the charges and is directly proportional to magnitude of two charges. What it means? French physicist Coulomb measured force between 2-point charges, and he observed force between 2-point charges is inversely proportional to, is varied inversely as square of the distance between them. Suppose distance between 2-point charges is r, the force varied inversely as square of the distance, and also force is directly proportional to product of magnitude of two charges. Or we can write Coulomb's law says force between 2-point charges, force between 2-point charges is directly proportional to product of magnitude of 2-point charges and inversely proportional to square of the distance between them. Or we can write force between 2-point charges is equal to some constant k into magnitude of product of two charges q1 q2 divided by square of the distance between them. This is the mathematical form of Coulomb's law. F equal to some constant k into magnitude of two charges divided by square of distance between them. How Coulomb measured force between 2-point charges? From his experiments. Coulomb used torsion balance to measure force between 2-point charges. This is the experimental setup of torsion balance. The best example for torsion is when a rope is fixed at one end and other end is twisted. That is the best example for torsion. Torsion means twisting. You can observe very thin wire here. This is the torsion wire. At the end of the torsion wire, there is a light horizontal rod. At the end of light horizontal rod, there are two metallic spheres, small metallic spheres. Consider these two metallic spheres. Other metallic sphere, the metallic sphere at other end is simply for balancing. Consider these two metallic spheres. Here one metallic sphere is free to move and another metallic sphere is fixed. When force acts between two charged metallic spheres, this metallic sphere which is free to move will twist, and angle of twist will give you the magnitude of force. Here is the scale. You can observe here. Here is the scale. When this metallic sphere which is free to move twists, angle of twist will give you magnitude of force. Here at the time when Coulomb was doing experiment, at that time there was no any electrometer. He needs different charges to do experiment. So what he did, initially one metallic sphere is charged, say Q, and another is uncharged. Say charge on another metallic sphere is 0. When these two uncharged metallic sphere come in contact with charged metallic sphere, they will reach electrostatic equilibrium. That means both the metallic sphere, they are of same type and same size. They will equally charged. They will become equally charged. They will become Q by 2 and Q by 2. This is how Coulomb got differently charged metallic spheres. When the charged metallic sphere, when having charge q by 2 come in contact with another metallic sphere, uncharged metallic sphere, again it will reach electrostatic equilibrium, charge will equally distribute, they will get charge q by 4, q by 4. This is how Coulomb got different metallic spheres having different charges q by 2, q by 4, q by 8 and so on. For he measured force between two metallic spheres for different charges q by 2, q by 4, q by 8 like that. And then he kept charge on the sphere constant and he varied distance between two metallic spheres, distance between two charged metallic spheres. Hence, Coulomb varied distance. By varying distance, he measured different readings. He measured force between 2-point charges. He observed force between 2-point charges varies inversely as square of the distance between them and directly proportional to product of magnitudes of two charges. In Coulomb's law, the constant K is given by K equal to 1 by 4 pi epsilon naught. Epsilon naught means permittivity of free space. How much it allows for electrostatic force in vacuum. That is the meaning of permittivity. Permittivity of free space. In SI units, the value of K is about 9 into 10 raised to 9 Newton meter per meter square per Coulomb square. F equal to constant K into magnitude of product of two charges by R square, where R is in meter and Q1, Q2 are in Coulomb, force is in Newton. SI unit of K is given by Newton meter square per Coulomb square. And the value of epsilon naught in SI unit is 8.854 into 10 raised to minus 12 Coulomb square per Newton per meter square. This is epsilon naught. Next is vector form of Coulomb's law. Now we can write Coulomb's law as force between two charges equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. If I write like this, it is incomplete information. Why? Because force is a vector quantity. So we should represent Coulomb's law in vector form. How to represent Coulomb's law in vector form? If we multiply unit vector to this magnitude, it will give you direction of force also. When we multiply unit vector to the magnitude, we will get direction of force. Then how to multiply unit vector? How to define unit vector? Observe here, can we write like this Q1 cap or Q2 cap? No, because here Q1, Q2 are scalar quantities and 1 by 4 pi epsilon naught is constant. Here direction of force is depending on displacement between two charges. Hence, if we multiply unit displacement vector, it will give you force including direction. Unit vector gives the direction of force here. Then how to define unit displacement vector? First of all, let us consider 2-point charges Q1, Q2. Let R1 be the position vector for charge Q1. R1 is the position vector. Position vector shows position of charge Q1 and also direction of charge Q1 relative to reference point O. Position vector shows direction and position of charge Q1 and also direction of charge Q1 with respect to reference, with respect to origin O. and R2 be the position vector for charge Q2. The direction of force, let us consider force on charge Q2 due to charge Q1. Force on charge Q2 due to Q1 is along this direction, and force on charge Q1 due to charge Q2 is along this direction. This is force on charge Q1 due to charge Q2. Here force on charge Q2 due to Q1 is along this direction. Here vector R2 minus vector R1 gives the displacement vector R21. Hence, displacement vector R21 equal to position vector R2 minus position vector R1. This shows displacement of charge Q2 relative to charge Q1. Here displacement vector shows displacement of charge Q2 relative to charge Q1, or we can also write displacement R12, displacement vector R12 as vector R1 minus vector R2. Displacement vector R12 can also be written as vector minus R21. Displacement vector R12 equal to minus of vector R21. Magnitude is same but opposite in direction. What we need here? Unit displacement vector, that is R21 cap. Let us find force on charge Q2 due to charge Q1. We shall find force F21. For that we need unit vector R21. R21 cap equal to, what is unit vector R21? Vector R21 by magnitude of vector R21. Here displacement vector R21 has both magnitude and direction. When you divide it by magnitude of vector R21, you will get purely direction. Hence, unit vector R21 gives direction, purely direction of force. Now, multiply this to force, you will get force including magnitude and also direction. I will write it here. Force on charge Q2 due to charge Q1 can be written as 1 by 4 pi epsilon naught Q1 Q2 by displacement vector R21 square. Here this is magnitude of displacement square into unit vector R21. Now this is Coulomb's law in vector form, because it gives force on charge Q2 due to charge Q1, which has both magnitude and direction. Or you can also write force on charge Q1 due to charge Q2. That is F12 equal to 1 by 4 pi epsilon naught Q1 Q2 by, just interchange the numbers, you will get force on charge Q1 due to charge Q2 R12 square into unit vector R12. This is force on charge Q1 due to charge Q2. Just to avoid confusion, I will only write this F21. Now you can easily write force on charge Q1 due to charge Q2. Here unit vector gives direction of force. Just for clarification, I will give you one example. From that you will come to know how unit vector gives direction of force. I am using this example to show you how unit vector gives the direction of force. Here there are 2-point charges q1, q2, both are 1 coulomb. q1 is at origin 0, 0 and q2 is at 3, 4. Here charge q1 is at origin 0, 0 and q2 is at 3, 4. Now we shall find force on charge q2 due to charge q1. Here q1 is at 0, 0, hence position vector r1 can be written as 0 into I cap plus 0 into j cap, and r2, position vector r2 is equal to 3 into I cap plus 4 into j cap. To find force F21 we need unit vector R21 cap. Before that we need displacement vector R21. Vector R21 equal to vector R2 minus vector R1, which is equal to, what is vector R2? 3 into I cap plus 4 into j cap, minus what is vector R1? 0 into I cap plus 0 into j cap. Therefore displacement vector R21 is equal to 3 into I cap plus 4 into j cap. This is displacement vector R21. And what we need? Magnitude of R21 also. Magnitude of vector R21 equal to, here, root of 3 square plus 4 square. Magnitude of vector R21, that is equal to 5. Magnitude of vector R21 is equal to 5. Here magnitude is mentioned. And also we need unit vector R21 cap. Unit vector R21 is nothing but vector R21 by its magnitude, equal to, what is vector R21? 3 into I cap plus 4 into j cap. 3 into I cap plus 4 into j cap divided by magnitude, that is 5. I will write it here. You will get 3 into I cap, 3 by 5 into I cap plus 4 by 5 into j cap. This is the unit vector R21. You can simplify it further. You will get 0.6 into I cap plus 0.8 into j cap. This is unit vector R21. This gives purely direction of force. Here it says the direction of force is 60% along x axis and 80% along y axis. If you substitute this in formula of F21, you will get direction of force also. I will use it. I will use this unit vector to find force. Therefore, force on charge Q2 due to charge Q1 equal to 1 by 4 pi epsilon naught Q1 Q2 by, here R21 square means magnitude of R21. R21 square into unit vector R21 cap. Now substitute the values. you know the value of constant, that is 9 into 10 raised to 9, and Q1, Q2 both are 1 coulomb. R21 is 5 here, magnitude of R21, 5 square 25, and unit vector R21 is 0.6 into I cap plus 0.8 into J cap. By substituting, you can get the force including magnitude and also direction. This is how unit vector gives direction of force. I hope it is clear now how unit vector gives the direction of force. Here there are some observations from Coulomb's law. First observation is force acts along the line joining the two charges. Force acts along line joining two charges, not in sideways. And second observation is nature of force depends on the sign of charges. If one charge is positive and another one is negative, it will become Q1, Q2 less than 0. If Q1, Q2 less than 0, you will get F as negative. That means if Q1, Q2 is less than 0, it shows charges are unlike charges. If charges are unlike, there will be attractive force. Force will be attractive. If Q1, Q2 is greater than 0, Q1, Q2 is greater than 0, then force will be repulsive. Force will be repulsive. That shows charges are like charges. If both charges are positive, Q1, Q2 will be greater than 0. Or if both charges are negative, then also Q1, Q2 greater than 0. If Q1, Q2 greater than 0, it shows force is repulsive and charges are like charges. And third observation is force obeys Newton's third law. Coulomb's force obeys Newton's third law. What Newton's third law says? For every action, there is an equal and opposite reaction. In Coulomb's law also, in Coulomb's force on charge Q2 due to charge Q1 is equal to force on charge Q1 due to charge Q2, but in opposite direction. Or mathematically, we can say force on charge Q1 due to charge Q2, F12 is equal to F21, force on charge Q2 due to charge Q1, but in opposite direction. F12 equal to minus of F21. These are the observations from Coulomb's law. We heard Coulomb's electrostatic Coulomb force is much more greater than gravitational force. We shall verify this interesting fact using one example. This example is given in NCERT textbook. Part of the example is given here. Coulomb's law for electrostatic force between two point charges and Newton's law for gravitational force between two stationary point masses both have inverse square law dependence on the distance between the charges and masses respectively. In Coulomb's law, force between two point charges is inversely proportional to square of the distance between point charges. And in gravitational law, in gravitational force, the force between the gravitational force equal to inversely proportional to square of the distance between two stationary point masses. Both have inverse square law dependence. Then what should we verify? Compare the strength of these forces by determining the ratio of their magnitudes for an electron and proton. We should compare these forces by finding ratio of their magnitude. The same question is mentioned here. we should compare two forces, electrostatic Coulomb force and also gravitational force. We know that according to Coulomb's law, force between 2 point charges is equal to 1 by 4 pi epsilon naught q1 q2 by r square. Here we should find force between electron and proton. Therefore, force between electron and proton is 1 by 4 pi epsilon naught constant. Charge on electron is minus E and charge on proton is plus E by r square, or I will write it directly. You will get minus of 4 pi epsilon naught into E square by r square. Consider this as equation 1. And we know that gravitational force equal to gravitational constant G into m1 m2. m1 is mass of electron and m2 is mass of proton by r square. Consider this as equation 2. Here let us consider magnitude of these two forces and let us find the ratio. Hence Fe by Fg equal to, consider only magnitude, 1 by 4 pi epsilon naught q1 q2 by r square by gravitational constant G into mass of electron into mass of proton by r square. Here r square cancels. You know the value of constant 1 by 4 pi epsilon naught equal to 9 into 10 raised to 9 Newton meter square per Coulomb square. That is 9 into 10 raised to 9 q1 into q2 E square, that is 1.9 into 10 raised to minus 19 square by gravitational constant G is 6.6 into 10 raised to minus 11 and mass of electron is 9.1 into 10 raised to minus 31 kg and mass of proton is 1.6 into 10 raised to minus 27 kg. If you simplify, you will get around 2.4 into 10 raised to 39. You will get around 2.4 into 10 raised to 39. Therefore, electrostatic Coulomb force is nearly equal to 10 raised to 39 times gravitational force. Hence, we say electrostatic Coulomb force is much more greater than gravitational force, because Coulomb force is nearly equal to 10 raised to 39 times gravitational force.